So before we start, I would remind our guests that there is the only way for you guys to interact in this webinar today. After the webinar or throughout the webinars, there is a question and answer box. You can click and ask some questions. We will try to answer depending on the question, whether throughout the webinars or at the end of the webinars. We have also prepared a presentation with reply to the question you post through the registration process. But let's start. 2 minutes in. Before I start, let me take a few moments to introduce ourselves. Introduce Bob. Bob is our guest speaker. He's been with us for more than, is that 2 years, Bob? Or am I going nuts?
What, doing this?
Yeah.
Oh, we've been doing this now for, I don't know how long, 3 years now?
Well, 3 years, it's been so long.
Yeah,
Okay.
yeah.
Yeah.
But I mean, I've been working with GMI for, oh God, I don't know how long, but a long time.
That's very long. But I was thinking, we started through COVID. So yeah, about 3 years.
Yeah.
So, Bob, besides working with GMI, he's a CompEx instructor and also an instructor of the ICX CompC scheme. And he's an inspector, and most of his experience, I guess, comes up from this inspection job. ULSTP committee is on, and I'm working with EX ever since. So he knows the standards in and out, the US standards as well as the international standards. In fact, the company has been also managing, it's called Source ICX. So, I has everything to do with the ICX. Sorry, Paolo, I didn't get it right. So I am Paolo. I work with GMI. I'm a sales manager here, and I take care of the big customer typically. But let me give you a small presentation on GMI, because he's sponsoring us, he's sponsoring this webinar, so we need to spend a few words. We are a company manufacturing, designing, and engineering intrinsically safe and SIL certified devices, which are used in most automation packages from DCS, ESD, fire and gas, and so on. In majority in oil and gas and petrochemical industry, but also pharmaceutical, fertilizer, mining, food, all over the world. We have over 40 years of experience. We're very proud to manufacture our product here in our facility in Italy, near Milan. But as I said, we are present globally through a series of subsidiaries. Next one. Around the world, from US, Middle East, Asia, and so on. We have channel partners or distributors globally. We're about 200 dedicated employees, and we have a lot of installation. Our PTR record is quite extensive, but at the same time, we have a small division that runs functional safety, EX, and cybersecurity training and services with the help of Bob or Tino. So because we make safety product, we try to make them as best as possible, because at the end, any of our product failure could lead to a disaster. So we make sure that they are manufactured using state-of-the-art technology. We have 100% traceability of our product, from the incoming components to the outgoing components. We have full testing, so every single item is tested 100% before it's shipped from the factory. The factory, they use an highly automated manufacturing process to keep our costs down and yet have reliability. To maintain a certain standard. In fact, we guarantee 5 years warranty and 10 years of availability. Next, so we make IS barrier, SIL 3 or SIL 2 certified. We have safety relay with or without line monitoring, SIL 2 or SIL 3. We have a line of isolators, so non-IX, SIL certified isolators, and power supply, which are EX certified and SIL rated. So we have power supply that are SIL 3 certified. One day you can look up one of our webinars on these power supplies. They are unique, and you need a SIL certified power supply if you don't think so. You look up the webinar that is being recorded and you see it. Multiplexer, line of art multiplexer, temperature multiplexer, digital multiplexers, series of termination panel designed to interface with all the system vendors out there, and then surge protection device, loop indicators, and as I mentioned, cybersecurity, functional safety, EX services and courses. I believe there is one more slide for me, Bob, which is our customers. So as I said, we can interface most of the system out there from ABB to Yokogawa and then one else in between. We are on the ADL of many oil and gas company. And we are proud to supply our product to many OEMs, which install our barriers or relay or isolator onto their machine, drilling rig, shipping vessels, wellhead packages, compressor packages, and so on. Okay, Bob, I believe this is my bit. I'll be listening to you here. And if you guys, as I said earlier, if you want to pose some questions, there's a box there for you to click in. Okay, Bob, so up to you.
All right. Well, thank you very much, Paulo. Thank you for the intro. So a little bit about fundamentals of EX. We're actually in, I realized this morning I'm wearing an Intertech shirt. So I'm actually today teaching a course. My colleague's actually taking over for right now, but we're teaching a Compex course for a bunch of engineers and designers over the next 5 days. So we're going to consolidate the 5 days of what we're doing in the full Compex design course into 45 minutes. So we'll kind of hit the high points and give you kind of a little bit of an overview on the fundamentals of EX in particular. So really getting down to the fundamentals, right? In order to have an explosive atmosphere, we need to address either gases and vapors and mists, combustible dust, ignitable solid particles. One thing that usually comes up when we're teaching these courses, people always think it's always the oil and gas industry, right? It's refineries and offshore oil platforms and everything else. But a lot of people don't realize that we're actually pretty much surrounded by hazardous locations in which a flammable gas air mixture or dust or particles are present, and they operate in many different industries. I was talking with a gentleman about bakeries, right? Because bakeries use dust. They have dust hazards, so they have to address it in a certain way. So you wouldn't necessarily think a bakery in particular would be a hazardous location, but there are parts of a bakery that are actually in that. I was talking to a gentleman last week about the automotive industry. They use a lot of solvents for paints and various materials that they're using. And so they're actually dealing with robots being suitable for hazardous locations. So there's hazardous locations all over the place that we don't necessarily always think about. So here's the important thing to remember about these explosive atmospheres in particular. Generally, liquids will not ignite. It's always the vapors. The vapors are usually the issue. So when we keep it in a liquid format, then we don't usually have problems. But unfortunately, to keep them from becoming vapors, then we have to keep them at usually extremely cold temperatures. And it's not practical in many cases. So anytime that we're using processing or moving or doing anything with flammable liquids, they will emit vapors. And the vapors are the issues that we have to deal with. And of course, these gases can be easily ignitable and very dangerous, and given that they can spread quickly and widely. So there's a term called flashpoint. And flashpoint is a term that we use a lot and we talk about. But basically, flashpoint is that temperature in which a liquid becomes a vapor, where it'll emit enough vapor to actually have an explosion if, in fact, it comes into contact with either heat or an electrical spark or something of that nature. So typically your flash points are different than the ignition temperatures. There's what is also called ignition temperatures or auto ignition temperatures of all these gases and vapors present in hazardous locations. So again, that's the temperature in which an ignitable amount of gas is emitted from a liquid. Ignition temperature is the temperature in which a gas will spontaneously ignite. So dust can be any of the following type of materials. Not all dust are flammable or explosive, but these are the typical ones. Metal dust, aluminum, magnesium, carbonation dust, coal, carbon black, charcoal, coke dust, and then certainly some of the other types like flour, grain, wood, plastics, and chemicals. Some of the first earliest hazardous locations that we actually figured out and had to deal with hazardous locations actually came from the coal mine. So some of the first protection concepts like intrinsically safe and flame-proof were actually developed in for the coal mines, because coal mines have a combination of both methane as well as coke dust, if you will. And both of them are extremely volatile, very dangerous. Let's move this. Only dust with stable oxides will not be combustible. So in order to have an explosion, right, we have to have three legs of what we call our explosion triangle. We have to have a source of ignition, we have to have fuel, and then we have to have something that's going to set it off, that explosive material. And that could be an electrical arc, spark, it could be heat, it could be static electricity, there could be any number of things that could be the catalyst, if you will, for igniting an explosive atmosphere. So we need to make sure that we understand all those types of energy that can be sources of ignition. So some of them are pretty obvious, right? Hot surfaces could be bearings, engine exhaust, damaged parts, friction, certainly lightning obviously can be a source of ignition. We had a train derailment that took place here in the United States here a couple months ago up in Ohio. And the train was carrying some volatile liquids, if you will, and it created a huge explosion. And they found that it was basically an overheated bearing that actually was the source of ignition in that particular instance. Obviously, things like open flames, fires, cutting torches, cigarette lighters, pilot lights. There's also things like mechanical sparks. There's limiting factors within the standards as far as types of metals that you can actually use, because you can actually get a reaction of banging two pieces of metal together, if you will. So we have to be very careful with the types of metals that we're actually using. Then, of course, there could be stray electrical currents, welding, electrical faults. Again, there's static electricity, pouring, dust, flowing liquids, conveyor systems, agitators, stirring liquids. All of those have to be addressed. What potential those could be for igniting a flammable atmosphere. And then certainly radio frequency, as we're becoming more and more tied into using Wi-Fi and local access networks in hazardous locations, and we have to deal with this as well. We have to be concerned about the radiated noise. Is there enough energy in which that can actually ignite gases and vapors or dust? And certainly things like batteries, ionizing radiation, X-rays, ultrasonics, exothermic reactions. Exothermic reactions, when we think about things like, for example, the ammonium nitrate explosion that took place in Beirut a couple years ago, that was storing, if you will, ammonium nitrate. And when that can actually become unstable when it's subjected to heat, and then it feeds upon itself, and then the next thing you know, you have a chain reaction, and therefore, in that case, a massive explosion. So again, we think about the obvious sources of ignition generally, but we don't necessarily take into account some of these other sources of ignition that generally can be just as dangerous, or in some cases are, again, things we don't necessarily think about, but we do need to take that into account in our projects and requirements and all that good stuff. So of the gases and vapors out there, and there's a whole slew of different gases and vapors that are flammable, we categorize these into various gas groups to make it easier for the selection of EX equipment. And we will group these based upon a couple different factors, one of them being the ignition temperature, but there's some other factors actually are much more important. But here's what some of the common gases and vapors that we'll actually see in industry, such as hydrogen. We consider that a 2C gas. It has an ignition temperature of pretty high, 560 degrees. Something would have to get extremely hot for it to ignite hydrogen from strictly a heat standpoint. And again, all these numbers will be located in the various relevant international documents and the IEC documents. You'll find them in NFPA documents. You'll find them in various other documents that will basically give kind of the relevant information on all these gases and vapors that we'll typically find in industry that we have to deal with. one of the big factors why we actually group these gases is actually the amount of ignition energy. Temperature is one thing, but the amount of energy that it actually takes to ignite a particular gas is something completely different. So if you look at our previous chart where it said hydrogen could be ignited spontaneously at a temperature of 560 degrees, on this slide, it's telling us that actually it only takes about 19 microjoules of energy to actually ignite hydrogen. It doesn't take an awful lot of energy to ignite hydrogen. So that's really the key reason why we put hydrogen and gases like acetylene in 2C. Some of the other gases we'll put in these other gas groups. The other traditional hydrocarbons will fall in those other gas groups based upon the ignition energy. When we talk about intrinsic safety, ignition energy is a key consideration because the whole idea of intrinsic safety is making sure that there's not a release of energy above that minimum ignition current or a minimum ignition energy, if you will. So minimum ignition and LEL and UEL. So LEL is the lower explosive limit. UEL is the upper explosive limit. All gases and vapors will have an LEL and a UEL. And generally speaking, most gases and vapors that you will find will have somewhere between a 2% LEL and 10 to 15% upper explosive limit. Within that area is the sweet spot, if you will, where if we have that mixture of fuel to oxygen, we have a source of ignition. At that point, we're almost guaranteed to have an explosion if, in fact, it's got enough energy. And in this case, what you're seeing on this slide, you'll see that propane has a fairly narrow band of LEL to UEL. It's about 2% propane to as much as about 11-12% propane. If we have that type of release into an environment, that mixture in conjunction with oxygen or air, and we have a source of ignition, we'll have an explosion. On the other hand, you see a wide band there with hydrogen, where hydrogen only takes as little as 4% hydrogen to as much as 77%, in which if we have that type of release into an atmosphere, and again, if we have 19 microjoules or more, we potentially could ignite hydrogen. So I know a lot of people were all talking about using hydrogen as a fuel now. There are some real critical things that we have to be very concerned with using hydrogen. It's a very efficient fuel, but it is also a very dangerous fuel that we need to take special precautions with. So our first poll question.
Yeah, so we want to make sure
What
you're
is the
awake.
definition of flashpoint? We'll see if you guys have been paying attention.
Yeah, I launched the poll. So what is the definition of flashpoint? Bob gave it away a few slides ago. So temperature in which a gas or vapor will spontaneously ignite, temperature in which flammable liquids will turn into a flammable gas, ignition temperature at which point the gas will explode violently. I would exclude this. The point in which a flammable solid will become a liquid. There's only one correct answer, guys.
There is only one answer.
Oh, and in fact, I think you can only click on one. We're not going to judge you. We, in fact, don't even know who clicks what. We just want to see in general, you know, if you've been listening or if we've been good enough at explaining. Let's put it this way. You know, it's always the teacher's fault if the pupil don't get it right. You know, it's always
absolutely, absolutely. It's always the instructor's fault, no doubt.
I see the answers as they come along. I don't see them, but I see them, and they are mostly right. Some are not. There's a 50-50 here, actually, with the two answer. And okay, since we are running into the webinar, I know you have a lot of questions. So let's stop it at this. And let me show you what you got. You got 50-50 between A and B. Only one of the two is correct.
Right, right. So the correct answer in this case is B. That's that temperature where a flammable liquid will emit enough vapor to turn into a flammable gas. That's our flash point. A is a good answer, but that's actually what is considered to be our ignition temperature. So here's the thing to remember: flash point will always be below the ignition temperature of a the flash point will always be below the ignition temperature of a gas. So for example, hydrogen, it is actually, its flash point, I think, is minus 254 degrees C, but its ignition temperature is 560 degrees C. So there's a big difference between when it becomes a vapor to ignite to where it will spontaneously ignite. So, and that's generally true for a lot of these gases and vapors or liquids that are liquid. It typically, we have to store them extremely cold temperatures. And if we don't, then we're going to have vapors going to be emitted from those gas or from those liquids that will become a vapor and then potentially ignite. So moving on a little bit, we also have to take into account the ignition temperature of the gas, and we actually put these gases and assign them a temperature class number. And this becomes important when we start selecting equipment for use in hazardous locations, because we also assign temperature codes for equipment. In this case, if we see something that is a T3 piece of equipment, what that's telling us is that the equipment will have an ignition temperature below 200 degrees C. If we see a T3 gas, that means that that gas will have an ignition temperature of above 200 degrees C. So in effect, what we're saying here, we can use a product that's a T3 product in a T3 environment. We can also use a product that might be rated T4, T5, or T6, because the relevant surfaces of those products under normal ambient conditions, under specified normal conditions or fault conditions, can actually not get above 200 degrees C. We cannot use a product that's rated T1, which tells us that it has a relevant surface temperature of something below 450 degrees in an environment in which the ignition temperature is, say, T3, which is something above 200 degrees. So we have to take this into account. This becomes extremely important when we have heat-producing devices like transformers, light fittings, rectifiers, those types of products, or we have gases and vapors that will actually have very, very low ignition temperatures. But we always have to take this into account, temperature classification.
Keep this in mind, this slide, because
So,
keep it in mind.
Yep. So if you'll notice, some of these gases and vapors have, there is not necessarily a relationship between the gas group and the temperature group. So some of the most volatile gases, hydrogen and acetylene, are actually have some of the highest temperatures in which they ignite. But some of the gases you'll see down on the far right-hand side, carbon disulfide, is about the only gas that's a T6 gas. That means that that gas, carbon disulfide, if we expose that in the correct mixture, that will actually spontaneously ignite at about 90 degrees C. So not too terribly hot. Carbon disulfide is one of those few items actually that which we require T6 equipment, because it is so easily ignitable based upon its auto ignition temperature or ignition temperature. So again, we'll assign a T code to all of these particular industrial gases and vapors, and that's where this comes from. So again, this chart is more or less just showing kind of what I've already explained. One thing you'll notice on this chart, and this, by the way, is right off the GMI wall chart that they give out for free. So if you want to get a copy of it, just make sure you drop us a note afterwards. We'll be happy to get this to you. But you'll see some T codes on the right-hand side, but then you'll see a T class with an asterisk, a single asterisk, and those are intermediate temperature codes. In the United States, for the division system, we have actually introduced and have used for many, many years now intermediate temperature codes, where in the international world, in ATEX, IEC, we basically just use the standard T codes of T1 through T6. So again, this is describing and telling us where we can use a particular product and how we're able to use it. Again, using T4 as an example, a product will never exceed 135 degrees C. A T4 gas will have an ignition temperature above 135, but below T3, which is 200 degrees C. Therefore, a T4 product can be used in a T4 or hotter ignition temperature gas environment. Another factor we have to take into with regards to hazardous location equipment and EX locations is the density of the gas that we are running into. So all gases could be lighter or heavier than air. You'll notice acetylene is one of those dangerous gases where it has the same density as air, almost roughly, meaning that if we release acetylene into the environment, it will go basically where oxygen or air goes. It'll go up or down, it'll go all over. If we're in an enclosed space, acetylene will get into all the nooks and crannies. Excuse me. And so we have to be very, very concerned about acetylene for that reason. Gasoline vapors, if you'll notice, it has a density of about 4, meaning that we actually, when we start filling up gas in our tanks, for those of us who are still using internal combustion engine vehicles, actually what we're standing in is a hazardous area, because as we pump fuel into our tank, we're basically, the vapors on the inside of the tank are coming out of the tank, and then they're collecting down near our feet. So this is why we always say, and you see this sometimes on YouTube, where people will use gasoline to start fires, and they'll pour gasoline and then take a couple steps back, but they don't realize that basically all those vapors have now accumulated around their legs. Next thing you know, they've set themselves on fire. So gasoline is heavier than air, so it'll travel along the ground until it finds a source of ignition or dissipates. So this is very important, where we're trying to determine where we're actually supposed to place things like gas detectors. So depending on the density of the gas, we're going to place them in different locations. So if the gas is heavier than air, then we're going to put a gas detector at a low point. If the gas happens to be lighter than air, then if it's an enclosed space, we might put them up in a ceiling or something like that. And of course, if the gas has the same density as air, we're going to be placing these gas detectors pretty much everywhere. So when we get into the design of some of our systems and understanding this, it starts to make better sense, if you will, based upon the density of the gas.
Here we have another poll question, guys. Bob discussed this extensively just a moment ago. What would be the T code for a product that has a maximum relevant surface temperature under normal or for condition of 135 degrees C? What will it be marked? T6, T5, T4, T3, T1, or none of those?
Yeah,
Again, only one answer.
Yeah, this is a little more difficult because we didn't. I showed what the numbers were, but we didn't really spend a whole heck of a lot of time on it.
Yeah, you know, 135 is between two codes. It's not on the right bench of one. You know, the upper one was 135, and the bottom was what, 110? No.
So I'll give you a hint here. T6 is 85 degrees C. T5 is 100 degrees C. T4 is 135, excuse me. T2 is, or excuse me, T3, I can't read. T3 is 200 degrees C, and T2 is 300 degrees C. So if that helps you make
25 is somewhere in between two, and it fits into one of them. He basically told you which one. Let me see if your answer came in a little more clear, because today we have other than T6, every single other has been clicked.
So,
but let me end it so we can move forward. It is actually T4, because T4 was 135, right, Bob?
That's correct. Yeah. So if a product is rated T4, that means its maximum relevant surface temperature will never exceed 135 degrees C. So if we have a product in which we've taken it, we've tested it, it will have a T4, because again, the relevant surface will never exceed that number. If a gas has a T4, that means the gas has an ignition temperature of above 135 degrees C or below the next number, which would be 200 degrees C. So that's the thing to remember from this.
Keep in mind, guys, we have a couple more of these poll questions, eh?
Yeah, just a few more.
Just a few.
So area classification, not to go through this slide completely, but basically we have to do an area classification on our facility to determine the frequency and duration. That's basically what we want to find out. And this is how we categorize it. So our protection level is going to be based upon the equipment. The definition is where you see, is it present continuously or during normal operation or maybe for a short period. So basically, if you think about it this way, if it's a continuous hazard, we typically call that a zone 0. If it's normal, it's going to be zone 1. If it's not present during normal, but it will be for a short period of time, it typically will be a zone 2. And then you see the dust hazard markings, and it's pretty much the same. What you will actually find on the right-hand side, those are the markings for equipment that are built under the ATEX directive. And then on the right-hand side, you'll see things for equipment that's built under the IEC EX scheme. These are the marking requirements that you'll find on pieces of equipment. And by the way, the IEC standard 10-1 and 10-2, the 60079 standards, actually state that you can use those two standards as your area classification, but you can also use other standards that are out there. So the Energy Institute IP15 is a great document for area classification. Actually, it's probably the most complete document for area classification. Within the United States, we also follow API recommended practices in certain markets, primarily for the offshore drill or production industry. And then NFPA is another document that we use here in the United States for area classification, typically for onshore facilities like refineries and chemical plants. So furthermore, we divide the equipment category designation, and this is where we get into our markings of equipment. And again, M1, M2, that's our mining, 1, 2, and 3 is surface equipment groups. G or D is gas and dust. And then in the IEC EX world, we basically have 1, 2, 3, or we have a mining, an M, a G for gas, or D for dust hazards. So again, kind of just to go back to that slide and show a little bit about what that all means. And again, here's our protection level. If we have a product that has a very high fault tolerance, then that product would be suitable for zone 0, single fault tolerance, zone 1, so forth and so on. So example, a lot of the GMI products you'll find that are suitable for zone 0, they are 2 fault tolerant, meaning that with regards to a barrier, you will actually find things like redundancy built into the barrier itself, maybe redundant Zener diodes, those types of things that you'll actually find to make them suitable for an environment in which it's flammable pretty much nonstop.
Okay.
So a definition of a zone 1 hazardous location.
So place where a gas or vapor hazardous atmosphere is present frequently or continuously, or is present occasionally during normal operation, or occurs infrequently, or is present occasionally during normal operation. But this is a different one. Place where dust hazardous atmosphere is present occasionally during normal operation. It looks like the same. So we have the gas or dust, or basically you have frequently, occasionally, infrequently, gas or dust.
Right.
Again, one correct answer. We're talking about zone 1, right?
Yep.
Zone 1, okay. Zone 1.
So I think you guys are getting this for the most part here. That's good.
Zone 1, we have zone 0 also, right?
So yeah, well, zone 0 defined is in here.
Yeah. So okay, because I haven't read this previously, so I'm trying to guess myself which is the correct answer.
Come on, Paulo, you know the answer.
Normal operation. Yeah, I imagine.
It's somewhat of a difficult
B
question.
is the right answer, Bob. Am I right or wrong?
What did you say? B?
B.
Yes. Yes,
Okay, I got it right. Thank
you
you.
got it right. Yeah. So
Okay.
B is the correct answer, right?
Because
A,
A would be zone zero.
that's correct. The key
Okay.
word is continuous.
Mhm.
C is normal operation but occurs infrequently. That's a zone 2. The issue is on D, when we talk about dust hazards, that is a definition for zone 21, not zone 1. So it's a
Right.
little bit tricky, right? So dust zones, we actually use 20, 21, and 22, where for gas hazards, we just use 0, 1, and 2. So
Okay.
a little bit of a tricky question there, but you got through it. So now that we've kind of figured out our gases, vapors, area classification, then we want to get into our protection concepts. And again, this is where we could spend a ton of time, but we only have a handful of minutes to be able to do this. But if you kind of break it down, the EX protection concepts are more or less, with all these different concepts that are out there, there are more or less 4 main categories. Energy limitation, which is intrinsic safety. This is where we limit the amount of energy. A non-sparking type device, or a device that basically will not spark whatsoever under normal or fault conditions, that's typically reflected by the concept increased safety. Things like containment. We contain an explosion, we allow an explosion to take place, but we contain it within an enclosure. That's typically done by flameproof. And then things like separation. We're removing a flammable gas from the source of ignition. Typically, that would be something like pressurization or maybe even oil immersion. So if we think about the legs of that triangle, what we're trying to do is, again, remove one or more of the legs of that triangle or deal with it in some way, shape, or form. For dust hazards, we have energy limitation, just like we do under gas. And again, intrinsic safety, or we have separation, which we call it dust ignition proof or pressurization or dust tight. Those are where we're trying to keep dust away from any source of ignition. So you'll see over on the right-hand side on that slide, you'll see there's a column there that says, start saying things like 60079-11 and so forth and so on. Those are the standards on which how to build something. So for example, the -11 standard is how to build intrinsically safe equipment. If I'm applying intrinsically safe, I don't necessarily need to know how it was built. I just need to make sure that it was certified, but I might need to know the standard right below, which is 25, which involves the design of intrinsically safe systems. So there's a lot of different IEC standards that are out there in the 60079 series of standards. Depending on your role and responsibility, you don't necessarily need to know all of them, front to back, but these are the product specific requirement standards that manufacturers are using to build their products and to meet the safety requirements for their equipment. So just to go through these a little bit more detail, energy limit, intrinsic safety, limit the amount of energy below the minimum ignition energy, and again, divided up into 3 ranges, depending on the fault tolerance, EXIA, IB, and IC. Non-sparking is an example called, the most common one is increased safety. So we have eliminated the potential for a spark or arc due to the design of the equipment. Excuse me. There's also what is called non-sparking, which used to be known as EXNA, is now known as EXEC, which was a lesser form of increased safety. The tolerances weren't quite as tight. The creepage and clearance distances, the impact resistant requirements, not quite as onerous, but it was only suitable for zone 2 applications, where increased safety was suitable for zone 1 and 2. Then containment, there's a flameproof box housing a bunch of components that are general purpose components in which the enclosure will breathe, will have a gas flammable atmosphere on the inside, and it will explode, but it'll be contained by the use of flame paths. And obviously we want to make sure that the covers are closed and all the bolts are sufficiently tightened and put into place. But some of the other containment concepts are things like powder filled or even enclosed break. So again, we're assuming we're going to have an explosion. This equipment will operate in a fashion to cool down that explosion to where it just doesn't go off and ignite the gas surrounding the piece of equipment. And then finally, some of the separation concepts. So encapsulation, where we're taking something and encapsulating it in a resin, could be some sort of epoxy. Down at the far right-hand corner, you'll see a ballast. So that was a typical protection method for a lot of components. You might see things like solenoid valves that might be epoxy filled. Again, ballast. Typically, you won't find large panels. They don't take them and fill them up with epoxy or anything else because there really is no maintenance associated with this. If anything fails, you basically have to throw it away and start over. There's some other concepts, hermetically sealed, where we're making the arcing or sparking separate from any gas coming into contact. Same thing with pressurization, where we're keeping gas vapors on the outside of our enclosure through the use of artificial pressurization. There's what is called oil immersion, and then finally restricted breathing. So all these concepts are basically separating the gas from the source of ignition. So this slide is basically just going to tell us a little bit about our EX marking to kind of give us an indication of how we'll actually mark our product and make it suitable for the environment, or determine whether or not it's suitable for the environment. So I don't know if you can see my mouse, but I won't get the little marker. But basically this part right here is your marking for the standard EX marking that is a requirement under IEC EX. This portion is the additional requirements that are a requirement under the ATEX directive. So just to go through this real briefly, we see a CE mark 0575. That's the quality, that's the organization that's responsible for the quality module of the manufacturer. This is the EX, that's the universal sign that this product meets the ATEX requirements. Roman numeral 2 is telling us anything above ground. So if we're not in the mining industry, that's above ground. This is what is called category 1. Category 1 is telling us that it's suitable for a high level, the highest level of protection. In effect, it's telling us it's suitable for zone 0. And then just to clarify, it's good for gas hazards. Then over here, this is the EX marking that we always have. The protection concept is intrinsic safety. This is telling us the gas groups that it's suitable for. This is telling us the temperature code that the product will be marked. And then finally, we have what is called the EPL, or equipment protection level, that is telling us that it's suitable for gas environments, and A being the highest level of protection. So putting all this together here is more or less telling us that our product is intrinsically safe, can be used in a zone 0 application as long as we meet the gas groups, which we will, because 2C basically includes all gases. And assuming that our ignition temperature of our gas is T4 or hotter, then we can use this product in any of those environments, and it has its ATEX certification. And down here, it shows its ATEX certificate, and then it shows its IEC EX certificate. So that's how we read our markings and labels and all that good stuff. So just to kind of put it together, I won't go through all of this based upon time, but just to highlight a couple lines on this thing here, you'll see at the very top right here, Roman numeral 2, 3, 1 in brackets or parentheses, G, EXNA, then you see this IAGI in brackets. That's telling us that this barrier is providing downstream protection into a device that's can go into a zone 0. And then what you see over here on the right-hand side, EXNA, that's telling us that we can actually mount this equipment in a zone 2 area, and again, providing downstream protection for a zone 0. Then we also have mining approval, we have dust approvals, and then we also have approvals for North American applications, including Canada and the United States. So this product basically, it can be used in most markets around the world, And it's basically an example of a label that you would typically find on an intrinsically safe barrier. Here's the labeling that you would find maybe on a flame-proof enclosure. So we have our part number here. We have our ATEX certificate here. We have our CE mark, our EX mark, our ATEX requirements right here. Again, surface industry, category 2, gas and dust. Here's our protection concept. Here's our dust protection concept. Then right below it, we have our IEC EX cert. Here's that same marking string all over again without the ATEX marking documentation that we would have. Here's our dust marking. Here's our IP codes. And in this case, we also happen to have an IEC EX certificate, which is referenced right there. So this is an example of a product that's certified both ATEX and IEC EX, and this is how a manufacturer would typically mark their product. So I think this is our last poll question.
Yeah, that was going to be a tough one. What best answer to describe the following EX marking string? I mean, you show it to us, but you know, it's not easy to memorize all of this, you know?
Right.
So 221 AX DB 2 CT 6 GBGA. Well,
So
there's a flame-proof enclosure suitable for 2C gas group located in zone 1. Flame-proof enclosure suitable for 2C gas located in zone 0. Flame-proof enclosure suitable for 2C gas containing increased safety relays suitable for zone 0. I mean, un pressurized enclosure suitable for second C gas located in zone 1 area containing associated apparatus. You need, you know, just on the marking, we need the lesson. I mean, it's
well,
thanks
yeah.
God we have that poster you mentioned earlier is available. You can keep it in your desk or on your whatever, on your iPad and look it up, because
And actually I think we have it on YouTube now. We do have a video that we actually went through the marking strings in detail.
okay, because it's
yeah,
and, you know, you are answering a lot of questions. I mean, every one of you is putting a different answer.
Yep.
None is clicking D, I guess.
Which is good.
I have no idea. Honestly, I have no idea what we're talking about. I mean, a second is the group you said, so it was gas, right? No.
Yes, this is a gas application. So
2 is the zone.
well, wait a minute. Roman numeral 2 is surface industry.
Surface.
Number 2 is category 2, which equates to a zone 1. But now we have a bracket where we have a 1. That means that there's something in that piece of equipment that's providing protection into a zone 0. Then the EXDB is telling us that's a flame-proof enclosure suitable for zone 1. Then within the brackets, it's telling us IA, which means that we actually have an intrinsically safe, or we have what we call an associated apparatus located inside the flame-proof box that's providing downstream protection into a zone 0. And it's suitable for all gas groups. It's suitable for all temperature codes, and it's suitable for installation into a zone 1 based upon the GB. So the correct answer here is actually A. It is a flame-proof enclosure suitable for 2C gases located in a zone 1 area containing associated apparatus, which is a fancy term, excuse me, for an intrinsically safe barrier. So this is exactly that application where we take an IS barrier, put it inside of a flame-proof box, and there we go. So,
all right.
By the way, this question,
an easy one, guys.
this question is actually one of the questions that we have within our IEC EX training and CompEx training. So it's
you better
don't
study
feel bad.
If you want to go for the training class.
Don't feel bad if you didn't get it right. It's not an easy one, right?
Okay.
So there is also, when I mentioned wall charts, GMI has a great hazardous location wall chart. We saw some pictures from that, but GMI also has a functional safety wall chart that's available as well.
Yep.
So Here's in this we didn't, I think I changed the summary, it has to be a little bit different here, but basically just the important thing to remember, right? Understand that we work and live and operate in hazardous locations, even though we don't necessarily think about it all the time. Remember this, there's different sources of ignition, and even simple little things like when you fill up a gas tank, right, or something like that, let's not really use our cell phones, because cell phones can be a source of ignition, right? But here's a big thing that I always see all the time, especially in Texas, right? We all have pickup trucks here in Texas. People will take gas cans and they'll fill them up on the inside of the bed of their truck. And sometimes these trucks will have bed liners, and all of a sudden it'll build up some static electricity. And there's some incredible videos where literally people are filling up these exterior plastic cans that are building up static electricity. Then they go and put the lever back to stop fueling it. They touch it, inadvertently, and they're grounding it in some way, shape, or form. And the next thing you know, you have a roaring inferno in the back of your pickup truck. So hazardous locations exist in areas that we don't necessarily think about all the time. And again, keep it in mind, be safe, don't do anything stupid. Always try to think twice before anytime we're dealing with any of these flammable gases and vapors, or even dust or fibers and flyings. Don't be the weakest link, right?
Right.
So we also have another presentation that we'll do, and let me see if I can bring that
I
up.
will show you this, Bob.
Okay,
That,
you're going to share that one?
because we have, you see it? So basically, guys, we still have 5-6 minutes. We will show you answer to the question you posed through the webinars. Okay, through the registration process. Now you still have a possibility to type some question in live, but I haven't seen any. What is the fundamental difference between flame-proof and increased safety, Bob?
Yeah,
The presentation, right?
Right, yeah. So flame-proof basically is where we take general purpose components, we can put them inside of a cast enclosure, and we're protecting it by the use of the enclosure with all bolts, finely machined flanges, all of that good stuff, flame paths, and will contain an explosion. Where increased safety, we're limited to basically using only certified equipment on the inside of, say, a plastic box or a sheet metal box. So we typically use increased safety for things like terminals, but there's a lot of equipment out there that are suitable for use in Zone 2, such as PLCs or HMIs, or even barriers, right? Or power supplies that are rated for Zone 2. Then instead of having to put them in big, heavy cast enclosures, we can now put them into sheet metal enclosures.
Great. Second question, what is the basis for zone classification?
Yeah, so it is a risk assessment based upon duration, the likelihood, and the frequency of flammable gas or dust being present. And again, what we use is the 6007910-1 for gases or dust, or some of these other documents. We subdivide based upon a source of release, an SOR, and we break it down into either a continuous source of release, which we consider a zone 0, a primary source of release, zone 1, and a secondary source of release is zone 2. So examples of zone 0 could be inside of a tank, zone 1 might be a pumping system, and then zone 2 might be flange joint in piping. So this is how we basically do our area classification, and all of the standards worldwide, no matter what you use, are all going to be basically based upon the same type of criteria. You may come out with slightly different numbers, but it's the same concept.
Okay. Does GMI manufacture product to relevant North American standard? Well, that's a biased question. We do.
Yeah. No, that was a question that came up, and I said, well, I'm going to answer it. Yes, GMI range carry North American approvals in addition to certification for most markets worldwide. How you can actually tell that it has a North American approval, if you see that little UL with a circle and a C on the left-hand side and a US on the right-hand side, what that means is that that's been certified by Underwriters Laboratories, and it's been certified to both the Canadian standards with the advent of the C on the left-hand side, as well as the US standards by having a US on the other side. So products will have ATEX, IEC, EX, as well as North American approval.
How does EX apply in automotive engineering? Oh,
Right. Yeah. And I mentioned this just briefly.
yeah.
We have an application going on right now where we're helping and assisting an individual that's doing with robots in solvents, right?
Yeah,
So,
because when you paint with solvent. It's one of our customer we have is robot manufacturers. Inside you have DO, basically DO barriers, because
okay,
the nozzle is driven by a solenoid. You have a solenoid open and closing.
right.
The solenoid it's IS, and it must be driven by a IS barrier.
And this is the same application. This is a company that doesn't build the robots, but they're building a unit that is used at the end of the robots to more or less clean, if you will, after some of these frames or some of the equipment has actually been gone through solvents and everything else, and they use solvents to basically clean it.
Yeah.
So basically, it's considered to be a zone 1 or zone 0. Well, I think it's going to be a zone 1 location.
To give you another example, of that kind of solvent, we sell to a company that manufactures printing press, where you take newspaper. It's a 20-meter long machine, and the paper comes in, newspaper comes out of the other end. Now, ink is solvent based, so all of the switches, on that control all the rolling, they are all in hazardous locations. So you have a lot of DI barriers on those things.
There you go. Yep. Yep.
Strange application. I want to get certified as competent under the ICES competency. Well, there you know. How can I do this? Well, just call Bob.
Yeah. So if you are interested, we're considered what is called an IECX recognized training provider. And the COPC is Certificate of Personnel Competency. And certain modules require just written exams. Others involve practical assessments. So regardless, and you can go to the IECEX website no matter where you are in the world, and you can do a search for what is called IECEX RTPs. You'll see it on the left-hand side of the IECEX website, and you can find various organizations like mine. Obviously, we're based here in the United States, but many of you are located in various parts of the world, and you can go through that whole process. And this is what a personnel certificate actually looks like. So this was mine in the modules that I went through and did all this good stuff. We don't issue the certificates. We're not allowed to do that. It has to be done by an IECEX certifying body. And so we work with an organization out of Canada called QPS, who in turn, we do the training, we do assessments, but yet QPS issues the certificates. You there, Paulo?
Stop for a second there. Can I a second by your back? Yes. Yeah, you're okay now. You're okay.
Oh, okay.
So can a barrier be installed in zone 2? It can.
Yes.
But either it must be certified for it, or you can place it into an.
Yeah. So as we mentioned, a lot of barriers will actually be rated now suitable for mounting in a zone 2. However, if we have to mount them in a zone 1, then generally we're going to have to take those barriers and put them inside a pressurized enclosure as one example, or put them in a flame-proof enclosure as another example. This does present an issue because when we're selecting barriers, we have to match the barrier to the device, and we have to take into account the total inductance and capacitance. So one of the things that people forget about when we take into account capacitance and inductance is the stored capacitance and inductance on your cable length. So the longer the cable length, the more potential energy storage. Therefore, we have to be very, very careful, and we start getting close to those minimum ignition energy curves, if you will. And we want to be very, very careful about that.
All right, Bob, that's great. We have reached the end of our webinar, and a lot of questions always come in. We are interested on this or that, so you can go online in our website. You can see the live webinar schedule. You can also see all the webinars that we did in the past. They've been recorded, like today, and they have been placed on our YouTube channel, gminternational.com, /YouTube, whatever. Now we have one last call with you guys for a second before you go. It's to know how Bob did, because please don't rate me, but rate Bob. We kept it right about an hour, so thank you guys for being with us. If you have questions in the future, you can always send an email. We will post, we will send you by mail copy of the presentation. We will, and that's it. No, I will stop condivision. No, sorry. Here we go. Termina sondaggio. One last click. Here we go. Thank you for your excellent and good. And Bob, thank you. We'll talk soon, I imagine, about another month before we talk again.
Yeah. And thank you so much, Paulo. And thank you very much for participating. I know this was a lot of information in 45 minutes, but hopefully there might be a little tidbit of nugget of information that maybe this will help you in your EX journey. But again, as Paulo said, please reach out to us if you have any questions or you need further information. Be happy to help you.
Bob, guys, bye. See you. Ciao, ciao.
All right. Take care. Thanks, Paulo.